Okay, last time we talked about arc length, and we did an example with a helix and some other thing that was too complicated to solve for. But let's take a look at the helix again. Should we write the arc length formula again, or are you guys good with that? So the helix cosine t, sine t, and t and we went from 0 to t to 2 pi, and then I think when we did it we got it to be equal to 2 pi. Was that correct?
Yep.
So was it this? What was it?
No, I think it was cosine sine 1. Yeah. And then the derivative, t was the first one, the derivative of t was the 1. Because then the derivative was sine cosine was 0.
Oh, then we might have done it incorrectly. All right, let's redo this problem again. Oh, that was the original problem? So that wasn't a helix
No, it was the t was a 1.
in the original problem?
Yeah, in the original one.
So that wasn't a helix, right? No, it's not even a spring. So what would cosine t, sine t, and 1 look like?
Blended sine t, cosine.
To be circle, how would you describe that circle?
Circular.
Circular. So if this is 1, and I went from 0 to 2 pi, it actually wouldn't be a helix. So I think that problem might have been done incorrectly. So if it was in fact 1, then this would have been just a circle which has circumference of 2 pi. So I was thinking about that after we did it in class, and I thought, well, that shouldn't be 2 pi. So a helix would have a different value for this, right? The z would change. And so a helix would have t in here. And that would be a circle that goes up around like that. And so let's redo this problem.
Well, last class we just proved that we could find the circumference.
What?
Last class we just proved that we could find the circumference.
We found the circumference of the circle. Yeah, so now let's actually do it with a helix. So this is a helix, and for us to find the arc length, we want to, what do we want to do? We want to take the derivative, which is negative sine t, cosine t, and 1. And then we want to find the magnitude of that. Sine squared t plus cosine squared t plus 1 squared. And sine squared and cosine squared is 1, plus 1 is 2. So let's just call it 2. So that is the number that goes into integrand. So your arc length is going to be the integral from 0 to 2 pi square root of 2 dt, which is square root of 2t from 0 to 2 pi, which is just 2 square root of 2 pi. So this is the arc length of a helix in from 0 to 2 pi rotation. Any questions about this? All right. I don't know if I told you this, but when you're doing a parameterization of something, there's a lot of different ways to parameterize the same curve. Did you know that? What I mean by that is that I can try to come up with another parameterization that's not this thing, and it would still draw out the same curve. So let's do another example. And it'll be set up kind of close to the same way here. But I'm going to change the t's into a 2t's. And then if I draw this out, maybe I won't go all the way up to 2 pi because that'll give me, you know, an angle of 4 pi. It'll give me twice as high. But if I draw this from 0 to pi, then I'm going to get the exact same curve, right? So if I keep this curve right here for right now, and then draw another curve, maybe do this one in blue, the first one in blue, and then I'll draw the other curve in red. I don't know if you guys can tell the colors. Can you tell? Maybe if I make this yellow. No, it's hard to see. Green. I think I can get rid of the background. Mine's black.
Did you try the bright colors with the black?
Oh, you know what else I could do is I make one of them thicker. Oops, sorry. Well, in any case, they're drawing the same thing, and I'm going from 0 to 2 pi, but if I take that first one out and then draw this from 0 to pi instead, then I'm going to get that same curve. So the point is that this is the exact same curve. So if I were to do this problem over here and take the antiderivative and set it up to find the arc length, I should get the same answer, right? So let's see if that's going to be the case. Let's take the derivative and then the magnitude. So this is going to come out with the factor of 2. For 2 of them, 2 cosine t, and then this is just a constant 2, and then the magnitude is going to be square root of all this added together. So there's going to be a square root of 2 squared factor for all of them, and then I'll have, after I factor out, I get a 1 and then a 1, so under the square root I still have a square root of 2. Is that right? Okay, so if that's correct, then I would integrate from 0 to pi of this constant 2 square root of 2 dt, and then this is going to give me a 2 root 2 t from 0 to pi, and then that's just going to go pi and then 0, so that's just 2 root 2 pi. So I get the same answer if I parameterize it differently. So it's important to note that there's a lot of different ways to parameterize curves. The same curve, you can parameterize the same curve, but if you find the arc length, it should still give you the correct answer, or the same correct answer, because arc length is arc length. That's the geometry of it, regardless of how you parameterize things. Okay? All right. Now, there's this concept where you can parameterize by what's called arc length. And let's see if we can look at the book for what they mean by this. So they say it's often and reparametrizing is not really a thing that we would do all the time. I think they just want to be able to get this idea of the parameterizing by arc length without actually doing it, because that's where some of the concepts kind of grow out of. So it's often useful to parameterize a curve with respect to arc length, because the arc length arises naturally from the shape of the curve and does not depend on a particular system. So if you parameterize a certain way, then it might be easier to look at things conceptually. Now, in practice, that's not an easy thing to do, not necessarily an easy thing to do. And again, if we stick with Helix, then we might be able to handle it okay, but then if you start going off doing all kinds of weird stuff, then it could be difficult. So it says here a curve R of t is already given in terms of a parameter t, then S of t is the arc length function given by that equation, and we should be able to solve for t as a function of s instead of s as a function of t. And the curve can be reparameterized by substituting the s variable in it. So what does that allow us? Let's see what that allows us to do. So this is your arc length function. S is equal to the integral. And then they changed the formula a little bit. Usually we go from A to B, and I'm going to change this, so I don't know if you want to write this down, but I'm going to erase a couple of things. R prime of t dt. So what they want to do is they want to write this as a function of t as you move along the curve t. And so what they do is they change a couple of things. Maybe instead of actually erasing it, I'll just scribble it out. They want to use the variable t for the upper limit. So that's the value that's changing. You can write this as now as a function of t. And then that means the t here can't be used because that's going to be a different variable. So they put another dummy variable here. Any variable you choose. They chose u. So now you can write this as a function s as a function of t is equal to integral from a to t and then the magnitude r prime of u du. Now they say, kind of casually at that, they say that, oh yeah, so if you just solve for t is equal to, if you solve for t is equal to a function of s, wait, how did they do that? T is some function of s where you solve for t, then you can replace your arc length function, and instead of calling it r of t, you call it r of that function with s. So now essentially your parameter is changed to s. Now s happens to be that special parameter called parameterized by arc length. It's the arc length parameter. And what that allows us to do is that if you have this curve R, this is A, I was going to say R of t, but we're reparameterizing it into something else. What this is saying is that if I move over here, say s is equal to 5, then this length over here is going to be equal to 5. And if I pick another s value over here, maybe s is equal to 12, then that means the length over here is actually equal to 12. So what they're saying is that as you move along this curve, if you're parameterized by arc length, as you move along this curve, whatever value, time value, or parameter value you're at, that's how long the curve you've drawn. Does that make sense? It's a hard concept. So, like I said, in practical terms, for general cases, finding this parameterization of arc length is nearly impossible. But for a helix, it can be done. So, do we want to see it being done with a helix? And then we'll say that was easy, that was cool, and it'll be hard for the other ones, and then we'll just move on. All right, let's try to do it for a helix. So the helix that we were looking at, we can look at either of these because they both give us the same answer. They both gave us the same arc length. So let's just choose this first one over here. Let's say we want to parameterize that helix by arc length. Whoops. Parameterize by arc length. So we want to set up that integral. We got all the steps down already, so I'm going to just remind us of what we got. Derivative magnitude turned out to be √2, was it? For the first one? Which is nice and constant. So because that's nice and constant, I'm going to write the integral, and then I'm going to change the parameters, the dummy variable after I write it. So you can either erase or cross it out. I have S is equal to, I'm going to leave some space here because I'm going to put of t. So S is equal to the integral from 0 to 2 pi, and I'm going to cross out 2 pi and change that into a t. And then I have a square root of 2 du or dt, and I'm going to change the t into a u. But this is an integral that we have, right? So now I'm going to change a few things to prepare to parameterize by arc length. I'm going to say S of t, cross out the 2 pi because I don't necessarily want to go that far. Call this t. And so now that I call this t, anything with a t inside of the integrand will have to change into a dummy variable, including the d2, dt, which is going to turn into a du. Now, if I work with this, let me rewrite this because it looks a little messy. 0 to t of square root of 2 du. And to integrate with respect to u, I'm going to have square root of 2u from 0 to t. And then if I put t in there, I'm going to get square root of 2t minus 0. Right? So now, what's nice about this is that I have this relationship with S of t is equal to square root of 2t. Or maybe I'll take out the S of t and make this into just an S. So if I solve for t, this is 1 over square root of 2 s. This is going to be the value that I can use for my arc length. What that means is that I can take this value and put it into R, So R instead of having my original parameter t, I'm going to have this go from go to 1 over root 2 s. So now my function is a function of s. What does that mean? That means my parameterization will be cosine of, instead of t, I'll put a 1 over square root of 2s. I have a sine t and then a t. And in all those places where I had a t, I'm going to replace it with this. All right? So that now is a reparameterization. I reparameterized it to draw the same curve. What does that mean? What good is that? That means when I draw this now, what was the arc length again? 2 root 2 pi. So what that means is that if I take this and I go from 0 to 2 root 2 pi, then I'm going to draw the exact same thing. That also means that if I go from r of 0 to r of, pick a number, 8, then the arc length from here to here is going to be 8. Okay? So that's the key about parameterizing by arc length. So this over here draws the same curve as the original r of t that we had from 0 to 2 pi. Maybe I'll put a star here to say that this is the star here that I'm talking about. It's the original curve that we're drawing from 0 to 2 pi. Once we reparameterize it, we can draw from 0 to whatever arc length we want to go up to. Okay? So that's parameterizing by arc length. So now it's not up to the parameterization, but now it's up to the geometry of your curve. The geometry of your curve dictates it. So let me finish this comment over here. This will have arc length of 8, because whatever number is in there. Provided I start with 0, because that's how I was able to reparameterize this. I started with 0. Okay? All right. So that is going to be helpful for us when we talk about curvature, because one of the definitions of curvature assumes that you will parameterize by arc length. Although, again, in practice, we're not going to do this. This just turned out to be really nice because it's a helix, and with a helix, we got constant, what do you call it? Constant length of the derivative. The velocity vector is not a function of t, which means it's a constant velocity. But if you change a function, your velocities will probably change. All right, let's talk about curvature now. So there's a couple of definitions for curvature. The first theoretical definition about curvature assumes that you can take a curve and parameterize by arc length. So the first definition of curvature actually takes a couple of things that we've just talked about. One of them is the idea of parameterizing by arc length. The other one is the unit tangent. Remember the unit tangent vector? The unit tangent vector is a tangent vector just made into a unit length. So one way to define curvature well, let's think about curvature. Let's draw a curve over here. And the idea is that at each point on this curve, we can define a numerical value, or we can find a numerical value that gives it its curvature, how much it curves or how it curves. Okay? So you can imagine maybe a point over here and a point over here would have two different values of a curvature. So just by looking at it, this looks like which one looks like it's more curved, A or B? This is A, and this is B. So B looks like it has a larger curvature, right? And then A looks like it has a less curvature. So how can we find the curvature, or how can we define the curvature? How can we talk about how much it curves? Well, one way to do that is with a tangent vector, because if we put a few tangent vectors near here, like maybe I'll do a tangent vector, I'm going to need to take off my glasses here. Tangent vector here, exactly at that point, and then maybe a point afterwards. And then we'll do the same thing for the next one. And if we see the way the tangent vector changes, we can kind of see a small difference of change here and a large difference of change here. So the tangent vectors don't change much. And then here, the tangent vector changes a lot. Now, if we're looking at vectors, remember the vectors have a point, a length and a direction, a magnitude and a direction, right? So in this context, we're really not concerned about the magnitude. We're just concerned about how the direction changes. We want to measure how the direction changes. And so if we take a look at this from a unit tangent point of view, the unit tangent vectors are always going to have length 1, so that kind of takes the idea of the length of the vector out of the picture, and we're just kind of focused on the direction, right? So that's one thing. The other thing to notice is that because if we parameterize many different ways, we can conceivably have a lot of different answers here for different values of t. So what if we fix it and parameterize by arc length instead? Then we have a more normal measurement of the curvature. So here's the first definition of the curvature. This, I would probably consider this a more theoretical definition of the curvature, because we'll find a more hands-on working definition where we can actually do computations. But curvature is defined by the change of the unit tangent vector with respect to by the way, in the future I'll say WRT with respect to the change of the unit tangent vector with respect to arc length. Now, before we write down the formula for this, let me just try to get one more thing kind of cleared up here. The change of the unit tangent vector with respect to the arc length. The unit tangent vector is a vector, right? And so we're taking the derivative of the vector. We take the derivative of the vector, what do we get? Another vector. So if we take the derivative of the unit tangent vector with respect to arc length, we're going to get a vector out of that. But we don't want a vector. We just want a numerical value for curvature. And so what do we do when we have a vector and we don't really want the vector? We want the numerical value. We just find the magnitude of that. And so get the magnitude. So the formula goes like this. This is a, I know it looks like a K, but it's a lowercase kappa, a Greek letter, which is K. And it's the derivative of the unit tangent vector with respect to the arc length, S. So in general, when you see S, you have to assume that it's arc length. Okay? So that's a curvature. Now, to be able to do this, what we need to do is we need to parameterize by arc length. We need to find a derivative and divide by the magnitude, which is the unit tangent vector. And so the biggest pain in the butt, I guess, to try to do this is to try to figure out how to parameterize by arc length, which, again, with the Helix, it's easy, but with everything else, it's not. All right, so we need another formula for this, and the other formula for this will just require us to use up some derivatives. And I don't have it off the top of my head, so I have to look at the book. There it goes. I suppose we could have used some calculus to figure this out, but turns out that the derivative of S with respect to t is, if we do the fundamental theorem of calculus, I guess we could have derived it. So here what they're saying is that the derivative of s with respect to t is just r prime, because s is equal to the integral from some value to t of the magnitude. I guess I just use single bars. Dummy variable. So the fundamental theorem of calculus says if we take the derivative of this with respect to t on both sides, then this is just going to be ds dt. And then d dt of this integral from a to t of whatever's inside. Well, I guess we should write down what's inside. So the fundamental theorem of calculus says if you have an integral from 0 or from a to the t, and you're taking the derivative of that with respect to t, it's just going to be whatever is inside of the integrand where you evaluate it by t. So that gives us a more functional formula to work with so that we can actually find the curvature at certain places. Okay? So this gives the curvature at a particular value. So should we find the curvature of a helix? Okay. So again, the helix is special. If you look at the helix, if you look at the spring going around, if you pick a point on the spring and then you pick another point on the spring, how do you think it's curved? It's going to be curved the same regardless of what point you're at. So for this particular, if we're going to do a helix, we're going to see that the curvature is going to be constant for any value of t that we select. Okay? We'll see that we'll see that the curvature is going to be constant. The t is not going to be important. So let's do that. Is my helix still here? All right, let's do this helix. So we can, curvature problems usually, they say find the curvature at a specific point. Otherwise, it could be kind of difficult unless it's a helix. So let's assume that we're looking for the curvature. Find kappa at 0 and kappa at 2 pi or something. So the kappa function requires us to find the derivative we got the derivative already. It wants us to find the magnitude. Got the magnitude already. What was it? Square root of 2 or something? What else does it want? It wants us to find, it wants us to find the derivative of the unit tangent. So let's go and make the unit tangent, which is going to be 1 over square root of 2 times minus sine t, cosine t, and 1. Now, since this is a constant, there's a list of properties that I need to, for derivatives that I need to show you guys. We'll do that in a minute. But since this is constant, then I can just leave this constant out and then take the derivative of the inside. So t prime is going to be 1 over square root of 2, and then I take the derivative of each of these things. Negative cosine t, negative sine t, and here I get 0. Right? And then let's take the magnitude. This is 1 over square root of 2. And then the magnitude of this is just cosine, sine. Which is going to be 1. So this is going to give us just 1 over square root of 2. All right, so what's the curvature? Kappa of t is equal to this thing, 1 over root 2. The magnitude of that, so just the absolute value. We don't need it because it's already positive. Divided by the absolute value of this, which is root 2. So that's 1/2. Is that right? I thought it was going to be 1. I think the answer is 1. Is there a mistake here somewhere? So the unit tangent is r prime of t divided by the magnitude of r prime t. And then the derivative of this is a constant times a vector. It's just a derivative of the vector. The t goes on top, the t prime. Anything else that could be wrong? Can you guys see anything? All right, let me think about this again. Is it really 1/2? Anything coming up? No? I guess we just assume that it's correct, huh? All right. Let's see if we could do a problem from, wait, before we do a problem from the homework set, there's a special curvature formula if you have y as a function of x as well. And actually there's several forms for this. So we'll say other formulas for curvature. This one involves a cross product. And so, I don't know, I probably wouldn't want to go into this one. But I don't know, it might be easier in some cases. So you can mess around with the different formulas of the... Hey, let's try this one since I'm doubting my other answer. Let's try this formula for that same problem. So we need the derivative and the second derivative, and then we want to cross them. And then take the magnitude. So let's find the derivative, which we already got. It's, what is it, negative sine t, cosine t. The derivative of t is 1. And then we need the second derivative, which is negative cosine t, negative sine t, and then we get 0. And then we want to cross them, r. I just wolframed it. All right. So let's cross them, r cross r double, or r prime dot, or cross, r prime dot, r prime cross r double prime. So I have r prime and r double prime already written up here, so I'm just going to go with this. So in the I direction, I have 0 minus negative sine t. That's in the I direction. In the j direction, I have 0 minus negative cosine t with a negative. And then in the k direction, I have sine squared minus negative cosine squared. So it's sine squared plus cosine squared, which is 1. And I think the magnitude of this is going to be square root of 2. So sine squared plus cosine squared is 1, plus 1 is 2, all under square root. So that's that. And then r prime, we already did this a while ago. R prime, the magnitude of r prime is square root of 2, and this is the denominator with square root of 2 to the third power. So kappa of t looks like it's square root of 2 divided by square root of 2 to the third power, according to this formula, and that is going to be 1/2. So I guess it was 1/2. All right. It might be worth it looking at a curvature of something else aside from a helix. So maybe we could take a look at a homework problem in 13.3. Oh, where's our curvature problems? Oh, they took their curvature problems and they here's one over here. That doesn't look easy. Wait, let me see if there's another one. No. All right, let's see if we can get through this one. Maybe we'll have Wolfram do the integral for us. No, we don't integrate here. We just need to find the curvature. So what we need to do is we need to find, I don't know which is going to be easier formula, but let's do the one with a cross product. Let's see if that one comes out to be easy. You got one shot at this. So let's take the derivative. This is 4t, and then the sine. Derivative of sine is cosine t. Now we have to do a product rule. So derivative of the first times the second plus the first times the derivative of the second. Might want to simplify that before I move on. And then the same business over here. So derivative of cosine is sine t, and then now I have the product rule again. Derivative of the first times the second plus the first times the derivative of the second. All right, so let me take a minute to simplify this. 4t, oh, that one cancels. That was nice. And I have a negative and a negative, so that's a positive t sine t. And then this also cancels. That's good too. And a positive, so that's a positive t cosine t. All right, maybe it's not so bad. So that's the first derivative. The second derivative, r double prime of t. The derivative of this is 4. This is a product rule. Derivative of the first times the second plus the first times the derivative of the second. And here, same thing, derivative of the first times the second plus the first times the derivative of the second, which is a negative sine t. All right, now we need to take the cross product. R1 cross, or R prime cross R double prime. So I have it right on top of each other, so I'm just going to do it from here. So the first component, I cross out the first column, and I do this cross here. This is going to be a little bit messy. You got t sine t times cosine t minus t squared sine squared t. Oh, minus. Oh, man. Now this is going to take too long. Because I have to subtract this, right? What? Is things going to cancel? Things are probably going to cancel. T cosine t sine t plus t squared cosine t. So that's just the first component. I did this minus this. Well, that is the first component of my cross product, right? Yeah. Yeah. All right, before we cancel, let's finish this. The middle term goes away. This is going to be a big negative term. You get 4t times cosine t minus 4t times t sine t. minus 4t cosine t. So that's the j term, and then the k term would be say it again. The negative should be this times this minus this times this, but then there's a negative in front of it because the j is negative. And then the k, let me just write down the k and then we'll just stop. The k is going to be 4t sine t plus 4t times t cosine t. Minus 4t sine t. All right, well, hopefully a lot of things cancel and this could be simplified so that we could take the magnitude fairly easily. And then the top one, the r prime, we need the magnitude of that as well. And then we just find the ratio of that. So, yeah, when it's not a helix, it gets a lot more difficult. There's no quiz tomorrow because we have an exam next week. So I don't know if I can get a review ready by tomorrow. But I'll try to get something done so that we can start reviewing over the weekend. All right.